Welcome to Deep Thinkers. Tonight, I want you to hold something in your mind that is smaller than a grain of sand, smaller than the period at the end of a sentence, so small that if it were resting on the tip of your finger right now, in the dark, you might not feel it there at all. And yet this tiny thing, this speck, is older than every mountain that has ever stood on this planet. It is older than every rock you have ever held, every cliff you have ever seen, every stone that has ever been shaped into a wall or a road or a grave marker. It is older than all of them by hundreds of millions of years. It is, as far as we know, the oldest surviving piece of the Earth itself. It is a crystal, a single crystal of a mineral called zircon, and it comes from a low range of red hills in the western part of Australia, a quiet and dusty place called the Jack Hills, in a region geologists have named the Narryer Gneiss Terrane. There is nothing dramatic about the landscape there. No towering peaks, no roaring waterfalls, just weathered ridges, dry scrub, ancient ground baked by the sun. A place you could walk across and never guess that you were stepping over one of the most important discoveries in the entire history of our understanding of the world. But there, locked inside an old sandstone, ground out of some vanished parent rock long ago and washed into place like sediment settling to the bottom of a stream, were these crystals. Tiny, durable, patient, waiting, and when scientists finally measured the age of one of them, the number that came back was almost impossible to believe. 4.4 billion years. 4,400 million years. Let that number move slowly through your mind, the way a cloud moves across the sky when you are lying on your back watching it. 4.4 billion. Our planet itself is only about 4.54 billion years old, which means this crystal, this grain smaller than sand, formed within roughly the first 150 million years of the Earth's existence. In the deep scale of the planet's life, that is almost the very beginning. That is the newborn Earth. That is a world so young it had barely started to become itself. So tonight, let this be the still point we return to again and again. A single crystal, older than any rock, carrying a message from a time we have no other way to reach. Because here is the strange and wonderful truth at the heart of this whole story. We have no rocks from that earliest age. None, the oldest actual rocks we have found, are younger than this crystal by a wide margin. The Earth, restless and hot and forever remaking itself, has destroyed nearly everything from its own infancy. It has melted its first crusts, buried its first stones, swallowed its first surfaces back down into itself. The record of the beginning was erased almost completely. And yet, one thing survived. One kind of crystal, tough enough and stubborn enough to outlast the destruction of everything around it. And it survived carrying a secret about what the young Earth was really like. A secret that, when we finally learned to read it, quietly overturned the story we had been telling ourselves for decades. But before we get to that secret, I want you to understand why a crystal, of all things, could survive when whole rocks could not. Because it is easy to imagine that a rock is more permanent than a tiny crystal. A rock feels solid, weighty, enduring. A crystal feels fragile, delicate, like something that might crack if you looked at it wrong. But the truth is the opposite. This particular crystal, zircon, is one of the most durable substances the Earth knows how to make. Its full name in chemistry is zirconium silicate. If you want the shorthand that geologists use, it is written ZSI04. And you do not need to remember that. What you need to feel is what that formula means in the real world. Zircon is a crystal built to last. It resists heat that would soften and melt the rocks around it. It resists the slow chemical weathering of wind and water and acid that dissolves softer minerals over time. It is hard. It is stubborn. It is the kind of thing that, when the mountain it was born in is worn away to nothing over hundreds of millions of years, simply does not wear away with it. Instead, it tumbles free, a tiny survivor, and gets carried off by ancient rivers, and settles somewhere new, and waits. And that is exactly what happened here. The crystal we are talking about did not form in the sandstone where we found it. That sandstone is itself extraordinarily old, around 3 billion years old, which is already almost unimaginable. But the crystal inside it is older still, by more than 1 billion years. Think about that gap. Picture the layers of time. The crystal formed. Then it survived long enough for its original home rock to be completely destroyed, worn to dust and grit. Then it was carried and buried and pressed into a new rock, the sandstone. And that new rock, itself 1 billion years younger than the crystal, then survived for another 3 billion years until human hands finally lifted it and asked how old it was. A crystal older than the stone that held it. A survivor inside a survivor. There is something almost tender about it when you sit with it long enough. The whole world it was born into is gone. Every trace of it erased, and this one small hard thing kept going, kept holding its memory, refusing to be forgotten. Now here is the part that turns this crystal from a mere curiosity into something profound. This zircon is not just old, it is a clock. A perfect, self-contained, unwind-able clock, and it has been ticking, in a sense, since the moment it formed. Here is how that works, and I will keep it gentle, because you do not need to be a chemist to feel the beauty of it. When a zircon crystal grows, when it first crystallizes out of hot molten rock, it is very particular about what it lets inside its structure. It welcomes atoms of uranium, it pulls them in, lets them take their place in the crystal lattice, part of the architecture of the thing. But it strongly refuses to let in lead. Lead is not invited. When the crystal is brand new, it contains uranium and essentially no lead at all. Keep that in your mind. Uranium, yes. Lead, no. That is the starting condition, the moment the clock is set. And then time does what time does. Uranium is radioactive, which is just a way of saying that it is unstable, that it slowly and steadily transforms itself, atom by atom, into other elements. And uranium, over immense stretches of time, decays into lead. This happens at a rate we understand extremely well, a rate as reliable as anything in nature, ticking along steadily, whether the crystal is buried a mile underground or resting in a laboratory drawer. So inside that zircon, from the moment it formed, a slow transformation has been underway. Uranium turning into lead, one patient step at a time, over billions of years. Now you can see the trick, the elegant, simple trick of it. When we find one of these crystals, and we measure how much uranium is left inside it, and how much lead has appeared, we are reading the clock. Because we know the crystal started with only uranium and no lead. So every atom of lead in there now had to have come from uranium decaying. Count the balance between the two, apply the steady rate we understand, and the crystal tells you its own age. It tells you, in effect, how long it has been since the day it was born. This method has a name. Geologists call it uranium-lead dating, or UPB dating for short. And when they held that method up to the oldest Jack Hill zircons, the crystals answered back, across the deepest abyss of time. 4.4 billion years. That is not a guess. That is not a story someone made up to sound impressive. That is a number the crystal itself carries, written into its own atoms, a message it has been keeping safe since the Earth was almost brand new. So already, just from the age alone, this crystal has given us something rare and precious, a direct physical object from the first 150 million years of Earth's life, a time we have no rocks from, a time that should have been lost forever. And you might think that would be enough. Just the age, just the survival, just the fact of it. But the crystal had more to say. It had a second secret, hidden even deeper inside it, and this second secret is the one that quietly rewrote the textbooks. Before I tell you what it was, though, let me pause here, because this is a good place to breathe. If you are settling in tonight, wherever you are, I would love to know where in the world you are listening from. Leave it in the comments if you feel like it, some quiet corner of the globe. A city, a country, a time zone far from mine. It is a strange and lovely thing to imagine all of us lying in the dark on the same old planet, thinking about the same ancient crystal, drifting toward the same sleep. And if you are new here, if this slow voice suits the way you like to fall asleep, you might quietly subscribe, so more of these long, calm journeys find their way to you. That is all. No hurry, let it settle, and let us go back down into the story. Now, the second secret. To understand why it mattered so much, you have to understand the story that scientists had been telling about the young Earth for a very long time. The story that this crystal came along and gently, patiently, took apart. For most of the last century, when people imagined the earliest Earth, they imagined hell. Genuinely, that is the word that got attached to it. The earliest chapter of Earth's history even got a name drawn from the underworld, an era called the Hadean, named after Hades, the ancient realm of the dead. And the picture that went with that name was exactly what you would expect. A world of fire. A surface of glowing, molten rock stretching from horizon to horizon. A global ocean not of water but of lava, seething and red, cracking and steaming under a sky choked with smoke. No oceans of water, no cool ground, no place a drop of rain could ever survive, because anything that touched that surface would flash instantly to vapor. A planet that was, for hundreds of millions of years, an unbroken furnace. That was the image. Hell on earth, quite literally. And it was not an unreasonable image, given what people knew at the time. The Earth had formed violently, out of countless collisions of rock and dust crashing together, and all that violence pours in enormous heat. The young planet would have been extraordinarily hot. So a molten, hellish beginning made sense. And there was one more event that seemed to seal the case. Very early in Earth's life, our young planet is thought to have suffered a collision so enormous it almost defies imagination. Another body, a world in its own right, roughly the size of the planet Mars, is thought to have struck the proto-Earth. Scientists have given this impacting world a name. They call it Theia. And the collision with Theia was not a mere dent or a crater. It was a catastrophe on a planetary scale. It is the event most scientists believe created our moon, flinging a vast spray of molten debris into orbit that gathered together and cooled into the pale companion we see in the sky tonight. But think about what such an impact would have done to the Earth itself. A blow like that would have remelted the surface of our planet completely. Any crust that had begun to form would have been shattered and liquefied. The whole outer Earth would have been turned back into a churning ocean of magma. The clock, in a sense, reset to zero, back to fire, back to hell. So there it was, a young Earth, born in violence, heated to melting, then struck by another world and melted all over again. Of course the early Earth was hell. What else could it possibly have been? The story felt complete. The name Hadean felt earned. And then came the crystal with its second secret, and it whispered something the story could not account for. Because locked inside these oldest zircons, alongside the uranium and the growing lead, was another kind of clue entirely. Not about age this time, but about the world the crystal was born into. It has to do with oxygen. Now, oxygen is not a single uniform thing. It comes in slightly different versions of itself, versions that weigh a little more or a little less than one another. Scientists call these versions isotopes, and again, you do not need the term, you only need the picture. Imagine that oxygen comes in a lighter kind and a heavier kind, mixed together. And it turns out that the exact balance of light oxygen to heavy oxygen inside a mineral is not random. It is a fingerprint. It records something about the conditions in which that mineral formed. In particular, it records whether the molten rock the crystal grew from had ever, at some point, interacted with liquid water at the surface of the planet at low, gentle, ordinary temperatures. Cool water leaves its mark. It shifts the balance, tilting it toward the heavier kind of oxygen in a way that molten rock alone never would. And when scientists measured the oxygen inside these 4.4 billion-year-old zircons, the balance was tilted. It carried the signature. It carried, faint but unmistakable, the fingerprint of liquid water, cool water, surface water. On an Earth that was supposed to be an ocean of fire. Sit with what that means, because it is genuinely one of the most quietly astonishing findings in all of Earth science. This crystal formed within the first 150 million years of the planet's existence, in the depths of that so-called hellish Hadean. And yet the chemistry it carries says that the rock it grew from had touched liquid water, that there was water on the Earth, that there were surfaces cool enough for water to exist as a liquid rather than a scalding vapour. Not a furnace world after all, or at least not only a furnace world. Somewhere on that young Earth, astonishingly early, there was cool ground and there was liquid water, and the crystal remembers it. The Earth, it seems, cooled far, far faster than anyone had dared to imagine. The hell, if it was ever quite so hellish, did not last hundreds of millions of years as an unbroken sea of lava. The planet may have cooled almost as soon as it formed, its surface hardening and calming within a geological blink, oceans of water gathering while our world was still, by every measure, a newborn. And this idea, born from the whisper of oxygen inside an ancient crystal, was given a name that stands in gentle opposition to all that fire. It is called the cool early Earth hypothesis. The idea, laid out carefully by scientists in the early 2000s, that after the great violence of its birth and the shattering blow that made the moon, the Earth cooled quickly and became a temperate, watery world remarkably soon, with only occasional reheating from the impacts that still rain down from time to time. Now, I want to be honest with you here, in the calm and careful way this story deserves, because the honesty is part of the wonder. The age of the crystal is about as solid as anything in science gets. The uranium-lead clock is trustworthy, tested, confirmed again and again. 4.4 billion years is a number we can stand on. But the interpretation of what that oxygen signature means, the leap from a tilt in the balance of isotopes to a whole cool, watery early world, that is a hypothesis. A very well-supported one. A leading idea, taken seriously by the people who know these rocks best, but an interpretation still rather than a closed and finished fact. The crystal whispers. It does not shout, and good scientists lean in to listen without pretending they have heard every word. That, too, is something worth carrying into sleep, that the deepest truths often arrive as whispers, and that it is possible to hold a thing as both wondrous and not yet fully certain, and to be at peace inside that uncertainty rather than troubled by it. But even held gently, as a leading idea rather than a proven one, the cool early Earth quietly changes everything about how we picture the beginning. Because the old story, the story of endless fire, had a certain grim simplicity to it. A molten planet slowly hardening over eons, like wax cooling in a mold, until at last, much later, the first land emerged. In that story, land was simply what you got when the fire finally went out. It was the default, the natural endpoint of cooling. Give the furnace enough time and it would harden into continents. The crystal tells a different story. It says the cooling happened fast, and the water came early, and if you follow that thread far enough, it leads somewhere unexpected and a little haunting. Because if the young Earth cooled quickly into a world of liquid water, if oceans gathered while the planet was still an infant, then the question is no longer how long it took the fire to harden into land. The question becomes something stranger and more beautiful. On a young planet that became watery so soon, where was the land at all? Was there any dry ground rising above those first oceans? Or was the newborn Earth, for a long stretch of its youth, a world almost entirely of water? A blue planet with barely a shore, an ocean world waiting for its first islands to be born. That is the direction this whole long night is going to carry us. Toward a planet that may have been nearly all sea. Toward the strange and wonderful realization that dry land. The very ground beneath you right now, the solid earth you have trusted your whole life, may not have been the default at all. That it may have been the exception, the rare thing, the hard-won achievement of a restless planet, land that had to be built, distilled, assembled, and lifted above the world's sea against the odds. That the continents are not where the story starts. They are what survived. But we are getting ahead of ourselves, and there is no need to hurry tonight. There is no rush to the end of this. Let us stay a little longer here at the beginning with the crystal, because there is so much still to feel in it. Consider, for a moment, just how much has been lost, and how thin the thread is that connects us to that first world. The Earth has spent 4.5 billion years remaking itself. It has melted and buried and recycled its own surface over and over, so many times that the record of the beginning is almost entirely gone. The oldest actual rocks we have, the oldest true stones, as opposed to isolated crystals, are younger than these zircons by hundreds of millions of years. Think of that. Even the most ancient rock we can find, and there are a few tucked away in remote corners of Canada and Greenland that reach back some 4 billion years, even those are beaten by the crystal. The crystal outlives the oldest rock by 400 million years. There is a real object, older than the oldest stone, and it is smaller than a grain of sand. And it is not as though these crystals are common, scattered thick across the ground for anyone to scoop up. They are staggeringly rare. Scientists sift through great quantities of that old Australian sandstone, separating out the tiny durable grains, dating them one by one, and only a precious few reach back to that oldest, deepest age. Each one is a single point of light in an almost total darkness. Each one is a window, no wider than a dust mote, onto a world we can reach in no other way. When you imagine the young Earth, you are not imagining it from photographs, or from written accounts, or even from layers of rock read like the pages of a book. You are imagining it, in the end, from a handful of crystals, from the atoms locked inside them, from the balance of uranium and lead, and the faint tilt of heavy oxygen over light. That is the thread. That is all of it. And it holds. There is a humility in that, I think, that is worth carrying with you into sleep. We are a curious species. We wanted to know what our own world was like when it was new, in a time before there was anyone to see it, before there were eyes of any kind on the whole planet, before there was so much as a single living cell, as far as we know, to witness the fire, or the water, or the first cooling of the ground. And we found a way. Not through grand monuments or great buried cities, because there were none, but through the patient reading of a nearly indestructible crystal that happened to survive. A speck of zircon carried the memory of the newborn Earth for 4 billion years and more, keeping it safe through the destruction of everything else, until a species clever enough and gentle enough to listen finally came along and asked it the right question. And the answer it gave was not the answer we expected. We expected fire, and it offered us water. We expected a hell that lasted ages, and it offered us a world that cooled and calmed with surprising speed. We expected the familiar story of land slowly hardening out of magma, and it began to hint at something far stranger, a young ocean world where the ground itself was the rare and precious thing. So let this be where we rest for now, before we go deeper. Hold the crystal in your mind. Smaller than sand, older than every rock, a clock of uranium turning slowly to lead, ticking since the Earth was young. A fingerprint of heavy oxygen whispering of cool water on a world we were told was made of fire. 4.4 billion years, patient and unbroken, carried across an ocean of time to reach you here, tonight, in the quiet dark, as you begin to drift. And the great question it leaves hanging over us, the question we will follow together through the long hours ahead, is a simple one to ask and a hard one to answer. If the young Earth became a world of water so soon, so early, so gently, then how did the land ever come to be at all? How did solid ground, real dry earth, ever rise from that first global sea? Where did the first shore come from on a planet that may have had none? That is the mystery. That is the long, slow descent we are about to make together, and there is no need to stay awake for the answer. The crystal waited 4 billion years to be heard. It will not mind if you fall asleep somewhere along the way. But before we make that descent, let me tell you how this crystal came to be in our hands at all, because the story of its survival is almost as strange as the story it carries. The rock that first held it, the mountain it was born inside, is gone. Utterly gone. Weathered down grain by grain over unimaginable spans of time, dissolved by rain and river, ground to sand and scattered. Whole ranges rose and were erased while this one crystal endured, and when its parent rock finally crumbled away to nothing, the zircon simply did not. It was too hard, too tightly bound, too indifferent to the forces that destroy almost everything else, so it was carried by ancient water, tumbled along the bed of some long-vanished river, and dropped at last into the sand of a younger world. That sand hardened into stone, and there it sat, a crystal older than every rock around it by more than 1 billion years, sleeping inside a sandstone that was itself 3 billion years old. a relic buried in something we would call ancient, and yet the relic was older still. This is why zircon is the messenger. Not because it is beautiful, though it is, but because it refuses to die. Zirconium silicate, a lattice so stable that it locks in its uranium and keeps it, and shuts out the lead that uranium slowly becomes, so that every atom of lead inside it is proof of time past, and nothing else. Nothing can be added. Nothing can be taken away without a trace. It is, in the truest sense, a clock sealed at the factory and never opened again, running quietly in the dark for 4 billion years, waiting for someone to learn how to read it. And when we learned, this is what it told us. Somewhere in Western Australia, in the low, quiet hills we call the Jack Hills, in the old rock of the Narryer Gneiss Terrane, these grains had been waiting, and their heavy oxygen, that faintly elevated signature we measure and call delta 18O, spoke of magmas that had touched water. Cool water. Surface water, not the searing breath of an open magma sea, but something gentler. Something that had already begun to resemble the world we know, and it had done so within perhaps 150 million years of the Earth's very birth. A blink, a single slow breath in the long life of a planet. I want to pause here, gently, because I would like to know where you are as you listen tonight. Somewhere in the world you are lying in the dark with this old story in your ears, and it would mean something to me to know where. So if you feel like it, leave a word in the comments and tell me where you are listening from. And if you are new here, if you have only just wandered in, you might quietly subscribe so the next slow journey can find you when you need it. There is no hurry. The crystal has waited this long. Take your time. Now, let us go back to what we thought we knew, and let us set it down softly, because it is not quite true. For a long time we told a certain story about the young Earth, and we gave that early age a fearful name. We imagined it as a world of fire without end, a churning ocean of molten rock beneath a sky that glowed. A place so hostile that nothing gentle could exist there for hundreds of millions of years. And there was reason for that image, real reason, because the Earth was born hot, born violent, assembled out of collision after collision as the young solar system sorted itself into worlds. The heat of that making alone would have been enormous. And then, near the very beginning, came the greatest blow of all. A body the size of Mars, a whole small planet we have given the name Theia, is thought to have struck the growing Earth in a collision almost beyond imagining. That impact tore material free and flung it into orbit, and from that ruin, in time, the Moon was gathered. But think what such a blow would have done to the Earth itself. It would have melted the surface anew, turned the outer world back into a sea of glowing rock, reset every clock, erased whatever calm had begun to form. If ever there were a moment that earned the name of a burning underworld, it was that one. And yet, here is the strange and beautiful thing, the thing the crystal insists upon. Even after a blow like that, even after the whole face of the planet was remade in fire, the cooling came fast. Not over ages beyond counting, but quickly in the deep time sense of the word. The rock hardened, the steam gathered and fell, and water pooled on the surface of a world that had so recently been molten. This is the idea that has quietly overturned the old picture. And it has a name of its own, the cool early Earth. When Valley and his colleagues looked closely at what those zircons were telling them, in the years after the turn of the millennium, they proposed that the young Earth had not lingered as a hell at all, that it had cooled and stilled, and grown a skin of solid rock, and standing water astonishingly soon, with only the occasional great impact to disturb the calm before it settled again. So the fire was real. But the fire did not last the way we imagined. The world we were taught to fear became, with startling speed, a world of water. A world of water. Set that idea down somewhere quiet in your mind and let it rest there for a moment. Not an ocean the way we picture it today, bounded by shorelines and headlands and the long gradual slopes where the sea surrenders to the land. Something different and older and emptier than that. A world in which those boundaries have not yet been established, because the land that would one day draw them has barely begun to exist. No beaches, no cliffs, no low-tide shelves of rock with their small pools and their slow creatures. Possibly no shores at all in any direction across the whole face of the planet. Just the movement of deep, ancient water under a sky that was not quite our sky, lit by a sun that burned slightly cooler and slightly yellower than the one we know, and over a floor of dark, basaltic rock that stretched from one edge of the world to the other without interruption. This is the picture that is slowly assembling itself from the evidence. Not from imagination, not from mythology, but from the chemistry of sediments laid down at the bottom of seas 3 billion years old and older. And from the isotopic signatures preserved in rocks that were once soaked in that ancient seawater and have never entirely forgotten it. And though the image sounds like something out of a creation story, a planet almost entirely covered in ocean, it turns out to be a conclusion that the Earth's own stones are beginning to tell us, quietly, if we know how to read what they are saying. In 2020, a team of researchers led by Benjamin Johnson and Boswell Wing published a study in the journal Nature Geoscience that leaned into this picture with particular force. They examined the oxygen isotopes preserved in ancient marine rocks roughly 3.2 billion years old, sedimentary material laid down in ordinary Archean seawater, and what those isotopes were recording. Written in the chemistry of the stone was a story about how water was distributed across the early planet. The argument they arrived at is still debated, as all arguments this old and this large tend to be, but it is taken seriously, and it is sobering. The early mantle, they suggested, held less water in its deep rock than the mantle holds today, which means more water was sitting at the surface, which means the oceans were larger, or deeper, or both. And if the ocean was fuller, and the crust had not yet built itself into the kind of thick, stable, high-standing masses it would eventually become, then the arithmetic tips in a single direction. The world floods, not through any catastrophe, not through any event with a name or a date, but simply because there is more sea than there is shelf on which to stand above it. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp, sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. There is a phrase geologists use for the small margin between land and sea. They call it freeboard. It is a word borrowed from shipbuilding, where it refers to the height of a vessel's hull above the waterline, the buffer between the ship and the sea it rides on. The thin strip of steel or wood that keeps the one from becoming the other. In geology, freeboard describes the equivalent for a continent. How far does the land stand above the level of the ocean's surface? And the answer, even now, even on a planet covered with mountain ranges and high plateaus and continental interiors rising thousands of meters above the nearest coast, is not very far at all. The average elevation of all the land on Earth today is somewhere around 800 meters above sea level. That sounds like a generous margin until you consider that the average depth of the ocean floor lies roughly 4 kilometers below that same surface. The ocean is not filling a basin that sits at the same level as the land. It occupies a floor that is fundamentally lower, held down by forces we will come to shortly, and the land rises above the ocean by a margin that, measured against the dimensions of the planet itself, is barely a scratch. Tilt that balance slightly, give the ocean a little more water, or give the continents a little less mass or a little less thickness, and the margin closes. The freeboard drops. The land that stands in the open air shrinks to a sliver. Drop it further still, and there is nothing. No shores anywhere. A complete world of water. In the early Archean, that may have been the condition of the Earth. Not for a brief moment, but for a very long time. And understanding how land eventually pulled itself above that waterline requires understanding something about the physics of rock. Because not all rock responds the same way to the forces that the Earth applies to it, and the difference between the two main kinds of crust that the planet produces is a difference so fundamental that it determines what persists and what vanishes, what accumulates and what is swept away, what the world remembers and what it forgets entirely. The floor of the deep ocean is made of a rock called basalt. Dark, fine-grained, dense with iron and magnesium, it is the rock that the mantle most naturally produces when it melts and rises to the surface. When you look at the geometry of a volcano erupting on the seafloor, pouring lava out across the dark basaltic plain at a mid-ocean ridge, you are seeing the Earth's default mode of making new crust. Not deliberate, not refined, just the simplest first step in a long chain. The magma rises, it cools, it solidifies into the seafloor, and it begins its slow journey away from the ridge, spreading outward across the basin as more rock is added behind it. Oceanic crust at the mid-ocean ridge is some of the youngest rock in the world. By the time it has travelled to the far edges of its plate, it may be 100 million years old or more, and in that time it has been cooling, contracting, settling deeper into the mantle beneath it, growing denser and heavier with every passing million years. And at the far edge, at the place where it meets the edge of another plate, that cold, dense, heavy rock finally sinks. It slides under. It descends back into the mantle. This is what we call subduction. And it is why the ocean floor has no memory. There is no piece of oceanic crust anywhere on Earth today that is older than about 180 to 200 million years. In places where spreading has been particularly fast, the seafloor is even younger than that. The ocean is in a state of continuous self-erasure, constantly making new crust at the ridges and constantly consuming it at the trenches, leaving no accumulation, no archive, no record that reaches back further than the last 200 million years. The entire sweep of time before that is gone from the ocean floor. The Permian, the Carboniferous, the Devonian, all the early chapters of multicellular animal life in the seas, gone, the late Proterozoic, the ancient Archean oceans full of microscopic life, gone, the Hadean seafloor, if it existed as a seafloor at all, gone, completely, without a trace, returned to the mantle long before any instrument could find it. The ocean remembers less than 200 million years. The Earth is 4,500 million years old. The gap between those two numbers is the scale of what the sea has forgotten. And yet the continents remember. In Canada's Northwest Territories, a body of metamorphic rock called the Narryer Gneiss has been dated to approximately 4 billion years. In southwestern Greenland, the Isua supracrustal belt preserves sedimentary and volcanic rocks ranging from 3.7 to 3.8 billion years in age. In Western Australia, within the ancient terrane we have already been visiting, the Jack Hill zircons carry dates of 4.4 billion years, and those crystals, as we have seen, were not simply resting where they formed. They had been eroded from mountains that are now entirely gone, carried by rivers and seas into a younger sandstone, and preserved there for 3 billion years without any deterioration worth measuring. The crystal is older than the rock that holds it by more than 1 billion years. And both of them survive. The rock of the continents survives not because it is sheltered from the processes that destroy oceanic crust. It survives because those processes cannot touch it. Because continental crust is made of different material, and lighter things float. Where oceanic basalt has a density of around 3 grams per cubic centimetre, continental crust, the pale, coarse-grained, silica and aluminum-rich rock that makes up the floors of old continents and the roots of mountain ranges, runs closer to 2.7 grams per cubic centimetre. It is lighter, not by a dramatic amount, but enough, because the mantle on which it rests has a density of around 3.3 grams per cubic centimetre or more. The continental crust sits on the mantle the way a wooden plank sits on water. You can push it down if you apply enough force. Press a mountain range against another mountain range, and the roots of both will dive deeper as the mass above grows taller. But the moment the force relents, the crust rises again. And if you try to push it far enough down into the denser mantle below, it bounces back. Because it cannot stay down. It is too light. The buoyancy is absolute, and over any geological timescale, it always wins. This is the reason there is any land at all. This is the reason the Pilbara Craton of Western Australia and the Karpfeil Craton of Southern Africa still sit in the open air after 3.5 to 4 billion years, their ancient rock worn smooth by every intervening era, but still present, still readable, still carrying the record of the early Earth in every grain and fold. Not because geology was careful with them, because they cannot sink. Because the physics of density and buoyancy does not offer subduction the option. Oceanic crust at 3 grams per cubic centimetre is only marginally denser than the upper mantle, but it is denser, and as it cools and ages, it becomes denser still. At the point of subduction, the old, cold, dense oceanic slab is actually slightly heavier than the mantle it is descending into. It does not need to be pushed, it falls. The weight of the descending slab pulling on the plate behind it is one of the primary forces that drives the whole system of tectonic motion in the first place. Geophysicists call this slab pull, and it is recognized as one of the most important engines of plate tectonics. The slab does not merely allow itself to be dragged down, it wants to go down. It is denser than what surrounds it, and it responds accordingly. Continental crust, by contrast, will not go. It has been tried. There are places on Earth where continental material has been driven partway into the mantle by the force of colliding plates, carried deeper than it would naturally sit, dragged down in the sutures of ancient collisions, and in every case, over time, it comes back up. The buoyancy is irresistible. You can bury continental crust, but you cannot make it stay buried. It always resurfaces. And this explains, with a kind of simple elegance, the contrast that might otherwise seem inexplicable. Why does the ocean floor preserve nothing older than 200 million years, while the continents carry 4 billion years of history in their bodies? Because one kind of rock can be destroyed, and the other cannot. Because basalt sinks and granite floats. Because the deep earth, which would happily consume everything if it could, is given only the heavy things to eat, and the light things are left behind. But here is the thought that should stop you for a moment, if you let it. That light, granitic, silica-rich continental rock is not the Earth's natural first product. It does not simply appear when a planet cools. If you take the mantle and you melt it and you let it rise to the surface, what you get is basalt. The dark rock of the seafloor, the dense, forgettable default output of a cooling rocky planet. That is what happens first, and in a simpler world that might be all that ever happened. The granitic rock of the continents is something else. It is a refined product, a distillate, something that required additional steps, additional chemistry. A process of selective melting in which water played an essential role, separating the lighter fractions from the heavier ones and allowing them to rise. Each cycle of this refinement produces rock that is fractionally more silica-rich, fractionally more luminous, fractionally lighter than what it started from, and the product of enough cycles, over enough hundreds of millions of years, is rock that can float. But the process requires the right conditions. It requires a planet with liquid water, and it requires some mechanism for pulling that water down into the deep rock, deep enough and hot enough for the selective melting to begin. Think of it as a kind of distillation in the old chemical sense, the way a still separates alcohol from water by heating a mixture until the more volatile fraction evaporates and rises, leaving the heavier residue behind. The Earth was running a similar operation, using heat and pressure and water instead of a copper vessel and a flame, and the product, after billions of years of slow separation, was the light rock that floats. The rock that remembers. The rock that stands above the ocean and refuses to go back down. In the very early Earth, before that process had run long enough to produce significant quantities of this refined material, the planet may have been covered almost entirely by the default product. Basalt, flooded by water, with nothing above the waves but the possibility of something different emerging, slowly, from below. A water world. A planet whose surface was ocean from horizon to horizon, where any land that existed was temporary and scarce, a narrow accumulation of lighter material that had not yet been fully refined or sufficiently thickened to stand reliably above the sea. And the sea was not a passive observer of all this. The water at the surface was participating, being drawn down into the cracks and fissures of the basaltic crust as it cooled and contracted, being carried deeper by the weight of overlying material into regions hot enough to interact with the surrounding rock, reacting with iron and magnesium, altering the minerals it touched, changing the chemistry of the crust in ways that would eventually influence how and where it melted. The ocean was not simply sitting above the story, it was writing it. There is something almost circular about this, and it is one of the deep puzzles of early Earth history. The process that makes continental crust, the process of drawing water into the deep rock and using it to selectively melt hydrated basalt and produce lighter material, that process, as we understand it today, is tied to a very specific geological mechanism. It happens at subduction zones, at the places where one tectonic plate descends beneath another, carrying water-bearing minerals with it into the hot mantle, releasing that water as it is heated, triggering the selective melting of the overlying rock, producing the chains of volcanoes that mark every subduction boundary. The growth of continents and the operation of plate tectonics are, in the modern Earth, inseparable. They are two aspects of the same process. Continents grow at subduction zones. Subduction zones require plates. Plates require tectonics. But on the early Earth, plate tectonics, as we understand, it may not yet have been operating. And yet something was making the earliest granitic rock. Something was producing the TT suite of ancient rocks, the tonalites and trondhjemites and granodiorites that form the cores of the oldest cratons. Rocks whose chemistry clearly shows they were made by the partial melting of wet basalt at depth. Whatever was drawing water into the deep crust and running the distillation was not necessarily the horizontal shuffling of mobile plates the way we know it today. It may have been something different, something older, something that the young Earth, with its hotter mantle and its thicker oceanic crust, was doing in its own way. Before the planet's interior cooled enough and the plates grew distinct enough for the modern regime to take over. And what that something was, and precisely when it gave way to the kind of tectonics we can map and measure today, is one of the questions that the evidence has not yet answered. The estimates for when plate tectonics began span a range that should give any confident prediction pause. Some researchers place the beginning as far back as 4 billion years, or even into the Hadean. Others favor a start around 3.2 or 3 billion years ago, and some argue that fully modern-style plate tectonics only stabilized relatively recently in geological terms, perhaps as late as 1 billion years ago, or even less. The spread between those estimates is more than 3 billion years. That is not a small uncertainty. That is the span of most of the Earth's recorded history, left open, unresolved, being argued over in papers and at conferences and across the field right now. But we are coming to that argument. We will spend time with it, because it deserves the attention. For now, stay with the ocean. Stay with the image of a planet that was, for a very long time, mostly water. A world without the continental shelves and the mid-ocean ridges and the familiar geography of basins and land masses that we carry in our minds from every map we have ever seen. A world where freeboard was negative or barely positive, where the margin between land and sea was so thin that a small change in ocean volume or crustal thickness could erase it entirely. Where the first granitic material, when it formed, rose into an ocean and found itself barely above the waterline, and perhaps not above it at all. Where the first islands, if they existed, were temporary and solitary and surrounded by a sea that stretched beyond any imaginable horizon. That image is not a dramatization. It is the best reading of the evidence we have so far, and it makes the ground beneath your feet seem different if you let it. Not obvious, not inevitable, not the default condition of a rocky planet, but something that had to be made, step by careful chemical step, over an unimaginable length of time. Something that almost did not happen, that depended on a precise balance between ocean volume and crustal thickness and mantle temperature, a balance that on another world, or on this world, under slightly different conditions, might never have tipped far enough to produce a single lasting shore. The land won. But it won slowly, and it won by building itself something that the ocean floor would never have. Not just a surface of light rock, but a deep root below it, a cold and rigid anchor hanging hundreds of kilometers into the mantle, holding the continent up and in place against every force that the churning interior could bring to bear. That root, the cratonic keel, the deep cold mantle structure that makes the oldest land unsinkable and permanent, is the part of the story that the surface never shows you. You cannot see it. You can only infer it from the way seismic waves move through the deep earth, from the chemistry of rock fragments that erupting volcanoes have brought up from those depths over hundreds of millions of years, from the simple fact that the oldest cratons are still here, still sitting in the open air after everything the planet has done to them. How those roots formed and what they are made of and why they resist the forces that would destroy them, that is what comes next. The roots of the cratonic keel are made of something called depleted mantle peridotite, rock from which the heavier, denser elements have been drawn off over vast spans of time, leaving behind a residue that is chemically lighter than the surrounding mantle and far more rigid, far less willing to flow. And because it is lighter and more rigid, it resists being dragged downward. It resists being heated and softened and churned back into the general mass of the planet's interior. It sits below the continent like an anchor that is also afloat, a structure that stabilizes what is above it while simultaneously refusing to be pulled beneath what surrounds it. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. And the question that follows immediately from all of this, the question the evidence opens as soon as you understand what the keel is and why it matters, is not how the keel formed. The question is, how much of the early Earth had one? How much of the early Earth was land at all? Because there is strong reason to think the answer, for a very long time, was almost none. Consider what the oxygen-isotope record from rocks approximately 3.2 billion years old actually suggests. In 2020, a study published in Nature Geoscience by Johnson and Wing used the preserved chemical signature of ancient seawater locked into those rocks to reconstruct something about the early Earth's water budget, specifically about how much water the mantle of the early Earth was holding inside itself versus how much was sitting on the surface. And the answer they found points toward a world in which the mantle, in the deep Archean, was storing less water than it does today. Less water underground. More water on the surface. A surface that, as a result, may have been nearly entirely covered by a global sea, with continental crust amounting to little more than a sparse scattering of islands, barely breaking the surface of a world ocean that stretched from horizon to horizon in every direction. This is the waterworld hypothesis, not a metaphor, not a dramatization, a model grounded in isotope chemistry, supported by the composition of ancient rocks, and consistent with everything else we know about the early planet, a hotter mantle, thinner and less abundant continental crust, a total ocean volume concentrated almost entirely at the surface because there was not yet enough subduction pulling water down into the deep earth and locking it there. A planet where dry land was not the starting point but the prize, where a shore was not a feature of the world, but an achievement. The distinction matters more than it might seem. Because the way most people imagine early Earth, a slowly cooling sphere, hardening from the outside in, with continents gradually crystallizing out of the magma like the skin on cooling milk, contains an assumption so natural it almost never gets examined. The assumption is that land is easy, that solid ground is what a rocky planet defaults to, and that oceans are the exceptional condition requiring explanation. The evidence says the opposite. Land on the early Earth was the exceptional condition. Solid ground above water, ground that stayed above water and did not simply sink back into the ocean under its own weight. Required a very particular kind of rock, formed by a very particular process, accumulated over a very long time in very particular quantities before it could stand permanently above the sea. That particular kind of rock is what geologists call felsic, or granitic, or continental crust, and it is different from the basaltic, mafic rock of the ocean floor in almost every property that matters for survival. Ocean floor, the crust beneath the deep sea, is dense, around 3 grams per cubic centimetre. It sits atop the mantle rather than floating comfortably above it, and it is thin, on average roughly 7 kilometres from surface to base, and the mantle beneath it does not treat it with anything resembling permanence. At subduction zones, where one plate slides beneath another, oceanic crust is dragged down and returned to the mantle, melted and reprocessed, within approximately 200 million years of its formation. The oldest ocean floor on Earth today is only about 180 million years old. Everything that came before it has been destroyed and remade. Continental crust is different. It is thicker, on average around 35 kilometres from the surface to its base, and far more than that beneath the great mountain ranges where plates have collided and crumpled the crust into double layers. And it is lighter, around 2.7 grams per cubic centimetre compared to the mantle's roughly 3.3. The difference sounds small. The consequence of that difference is vast. Because the continental crust sitting atop the mantle is too buoyant to be pushed down and kept down. It floats. Not the way a wooden plank floats on water, exactly, but by the same underlying principle, it is less dense than what surrounds it, and the result is that no amount of tectonic force can permanently subduct it, permanently consume it, permanently return it to the interior the way oceanic crust is returned. It rises back. It persists. The seafloor forgets. That is perhaps the cleanest way to put it. The seafloor is recycled so thoroughly and so continuously that nothing older than roughly 200 million years remains anywhere on the ocean bed. The entire deep-sea record of the first 4 billion years of Earth history has been erased and written over again and again, without mercy. But the continents remember. The Pilbara Craton in Western Australia carries crust that is 3.6 billion years old. The Karpval Craton in southern Africa is similarly ancient. The Acasta Gneiss in the Northwest Territories of Canada has been dated to just over 4 billion years. And the Jack Hill zircons, older still, were once part of rocks that no longer exist. But the crystals survived, eroded free, and settled into younger sandstone, carrying their locked chemical memory forward across a billion years of geological change. All of that survival, all of that memory, depends on buoyancy, on the chemical difference between continental and oceanic rock, on the fact that the early Earth, in distilling lighter material from its heavier interior, drawing off silica and aluminum and feldspar through repeated episodes of melting, of water being driven into hot rock and triggering a different kind of melt, a lighter kind, was performing a kind of planetary alchemy whose product could not be destroyed. You can erode a continent. You can bury it, thicken it, metamorphose it, fold it, stretch it. But you cannot, in the end, push it permanently down into the mantle, because it will not stay. And yet, The balance on which all of this depended, the balance between how much continental crust existed, how thick it was, how buoyant the mantle was beneath it, and how much water sat on the surface versus locked inside the rock, was for a very long time far more precarious than it looks today. Geologists call this balance freeboard, the degree to which continents sit above sea level rather than below it. And freeboard is not guaranteed. It is not a fixed property of the Earth. It depends on the total volume of water at the surface, on the total volume and average thickness of continental crust, on the density and temperature of the mantle beneath. Tip that balance in slightly different directions, and the result changes entirely. A little more surface water, a little less continental crust, a slightly warmer and more buoyant mantle, and there may be no beaches at all. There may be no land. The whole planet covered by a global sea, with the continental crust sitting just below the waterline, invisible, present, but not emergent. Not yet quite enough to break the surface and hold. That, as best the evidence can tell us, may be very close to what the Earth once was. So the question that follows naturally, that rises almost of its own weight from everything the evidence has so far suggested, is this: if the planet was once nearly all ocean, if the continental crust was present but thin, if the freeboard was so precarious that a small shift in any direction might have kept the whole world drowned, then how did land ever win? How did the crust grow thick enough, light enough, permanent enough to push above the surface and stay there? What was the process by which a water world, slowly and over an almost incomprehensible length of time, began to grow its own islands? The answer is not simple, and in the honest telling of it, there is a kind of loop at the center of the story, a circularity that geologists have spent decades examining and have not yet fully unwound. But the answer begins, as so many answers in the deep history of this planet begin, with water. With the movement of water downward. With what happens when water that belongs on the surface finds its way into rock that belongs to the deep interior, and what that rock then does in response. To understand this, it helps to hold in mind two kinds of crust side by side. There is the oceanic kind, thin, dense, dark, basaltic, the floor of the sea. And there is the continental kind, thicker, lighter, pale and silica-rich, the stuff that makes up the bedrock beneath every continent and every mountain range. The oceanic crust forms relatively simply, where mantle rock rises at spreading ridges and partially melts, producing basalt, a dark magnesium and iron-rich lava that cools into a solid, heavy plate. That plate is heavy enough, given time and cooling, to be pulled back down into the mantle. It is recyclable. It is not permanent. The oldest oceanic crust on Earth today is nowhere older than about 180 to 200 million years, because everything older than that has long since been dragged back into the interior and consumed. The continental crust is different in almost every way that matters. It is not primarily basalt. It is something called granitic or felsic rock, richer in silica, in aluminium, lighter in color, lighter in density. Its average density sits around 2.7 grams per cubic centimeter compared to roughly 3 grams per cubic centimeter for oceanic basalt. And that difference, that small, seemingly modest difference in density, is the difference between a planet with land and a planet without. Because the mantle that underlies the crust has a density of about 3.3 grams per cubic centimeter or higher. Continental crust, at 2.7, floats on it. It cannot sink. not in any permanent sense. You can push it down temporarily under the weight of another continent colliding or under the load of a great ice sheet, but it will rise again. It is buoyant, and buoyancy in this case is the same thing as immortality. But this lighter rock, this granitic, silica-rich, buoyant rock, does not form by the same simple route that produces basalt. It cannot be generated merely by melting the mantle and letting the lava cool. It requires something more. It requires a step of distillation, a process by which a rock that already exists is melted again under specific conditions and produces something chemically different. And those specific conditions require, almost always, the presence of water. This is where the loop begins to show itself. The oldest continental rocks that geologists have been able to study in any detail, not the isolated zircon crystals, but actual bodies of rock large enough to map, to sample, to read in cross-section, belong to a suite of compositions that go by the name TG. Tonalite, trongemite, granodiorite, three related rock types, all part of the same chemical family, all characterized by their relative richness in silica and their relative poverty in magnesium and iron. They are pale rocks. They are old rocks. Life was present, possibly, when the first islands were still being assembled from the distillation of granitic material rising through a hot, wet, vertical early earth. The first living things, if the interpretation is correct, would not have looked out over a world of established continents and familiar continents. They would have inhabited a water world in which the first scraps of dry land were still being pieced together from a process that had barely begun. This remains, to be clear, deeply uncertain. What is not uncertain, what is anchored in rock and chemistry as solidly as any fact in this story, is the age of the oldest intact piece of the planet's crust. Not a crystal, this time. Not a survivor sifted out of eroded mountains and buried in younger sandstone. An actual rock, a coherent assemblage of minerals locked together in the geological sense, preserving within its fabric a record of the processes that formed it. The Acasta Gneiss. It lies in the northwest territories of Canada, in a remote landscape of lakes and boreal forest, and exposed Precambrian bedrock. And it has been dated to approximately 4 billion years old, 4 billion, perhaps 4.03. It is a gneiss, which means it is a metamorphic rock, a rock that was heated and deformed after its original formation, its original minerals recrystallized under pressure into the banded, streaky texture that gives gneisses their characteristic appearance. It started as something else, probably a granite or a related igneous rock, and was subsequently cooked and squeezed into what it is now. But the zircon crystals within it have been dated by uranium-lead methods, and they give ages clustering around 4 billion years, making the Acasta Gneiss the oldest known intact rock on the surface of the Earth. 4 billion years. It is a number large enough that it resists feeling real, and yet there is something almost intimate about the Acasta Gneiss, something that the crystals of the Jack Hills, for all their greater antiquity, do not quite provide. A crystal is a remnant, a survivor, a fragment of something else that has been erased. The Acasta Gneiss is a piece of the planet that has held together, that has survived as a coherent body of rock through 4 billion years of geological change, through billions of years of the very plate tectonic and thermal processes that should, statistically, have destroyed or recycled it long ago. It is a survivor in a different sense, not the microscopic indestructibility of zircon, but the geological luck and structural integrity of a rock formation that happened to be part of a craton happened to be attached to a deep and stable mantle root, and happened to endure while everything around it was erased and overwritten. And yet the Jack Hill zircon is 400 million years older. The oldest crystal predates the oldest rock by 400 million years. 400 million years is longer than the time from the first fish to the present day. It is a gulf of time so vast that the planet could have gone through multiple complete cycles of geological activity between the formation of the crystal and the solidification of the oldest rock that still survives. Whatever happened in those 400 million years, whatever crust formed and was destroyed, whatever oceans cycled through and were renewed, whatever early attempts at stability were made and undone, is missing from the direct record. The crystal is the only voice from that time, and it speaks not through its bulk or its structure, but through chemistry, through the oxygen isotopes locked in its lattice, through the whispered record of a surface that was cooler and wetter than anyone had expected to find in a world that had only just survived a planet-shattering impact. This is the architecture of what we know and what we do not know. It is worth holding it all together now, in the quiet, and letting the sequence settle. The Earth formed approximately 4.54 billion years ago, assembled by gravity from the same cloud of gas and dust and pebbles that built everything else in the inner solar system. Shortly after its formation, the precise timing is still debated, but the best estimate is around 4.5 billion years ago. A body roughly the size of Mars struck the young Earth in what researchers call the giant impact, named for the hypothetical impactor Theia. The collision was catastrophic by any ordinary measure. It would have remelted the surface of the planet into a magma ocean, vaporized a significant fraction of the crust, and ejected into orbit the debris that would coalesce into the Moon. The clock, in many respects, was reset. And then, and this is the thing the popular story almost never says, the clock began running again. Very quickly. Within perhaps 100 to 150 million years of that reset, the surface of the Earth had cooled enough for liquid water. Not everywhere, perhaps. Not continuously, perhaps. The early record is too incomplete for that level of certainty, but the evidence from the oxygen isotopes in the Jack Hill zircons, particularly the elevated delta 18O ratios in grains dated to around 4.3 to 4.4 billion years ago, points clearly toward low-temperature interaction between these magmas and liquid surface water. The cooling early Earth hypothesis, developed and defended by Valley and his colleagues and published in Geology in 2002, proposes that the Hadean was not the prolonged uniform hell of fire and lava that its name implies, but something more complicated, a world that cooled from catastrophe faster than expected, with liquid water pooling in the basins of a young surface even while the interior was still searingly hot, and the impact flux from space was still high. Above that cooling surface, a near-global ocean likely spread. The evidence from later rocks, from oxygen-isotope studies of rocks around 3.2 billion years old, from the modelling work published in Nature Geoscience in 2020 by Johnson and Wing, suggests that in the early Archean the mantle still held less water than today, with the consequence that more water sat at the surface. More ocean, less land. The freeboard balance, the delicate ratio between total ocean volume and the buoyancy and thickness of the crust that determines whether rock stands above sea level or lies drowned beneath it. may have tipped for a long time towards submersion. The early Earth may have had essentially no dry land, or only the most fleeting and unstable of emergent surfaces, scraps of volcanic material briefly above the waterline before erosion and isostatic adjustment pulled them back under. And then the distillation began. Somewhere in the hot, wet, churning interior of that early ocean world. In the processes that cycled water down into the crust and used its chemical power to selectively melt the hydrated basalt and extract silica-rich, aluminium-rich magmas, the first continental crust was being manufactured. The teak rocks, the tonalites and trondhjemites and granodiorites that make up the bulk of the oldest surviving Archean terranes, were being generated by partial melting of wet basalt at depth. The exact mechanism, whether it required something resembling subduction from the beginning, or whether it could operate in a stagnant or squishy lid regime through sagduction and the slow downward pull of dense volcanic piles, is the question that researchers are still arguing at Isua and in dozens of other ancient terranes around the world. But the result is not in dispute. Light, buoyant, silica-rich crust was being produced. And because it was light and buoyant, it could not be subducted. It could not be recycled. It floated, and it accumulated. Slowly, over hundreds of millions of years, enough of this buoyant material gathered in particular regions to build something more than a transient volcanic island. The crust thickened. As it thickened and cooled, the mantle immediately beneath it, the lithospheric mantle that moves with the crust as part of the same tectonic unit, cooled as well and became chemically modified. The melting that had generated the granitic magmas above left the residual mantle rock depleted in its iron and heavy elements, lighter and more rigid than the surrounding mantle. This depleted residue accumulated as the cratonic keel, the tectosphere, extending downward from the base of the crust for 150, 200, 250 kilometers and more. An enormous cold anchor hanging beneath the growing land. The keel is what made the cratons permanent. Without it, the buoyancy of the continental crust alone might not have been sufficient to ensure long-term survival against whatever tectonic processes were eventually going to operate on the planet. With it, the cratons became something more like geological ballast, thick, cold, rigid. Chemically distinct, too buoyant in their upper parts to be subducted, and too dense and stable in their lower parts to be disrupted by convection or drowned by the weight of the overlying rock. The oldest surviving continental crust on the planet, the 4-billion-year-old Acasta Gneiss, the 3.6-billion-year-old cores of the Pilbara and the Karpfal, sits atop keels of depleted mantle that have been attached to it for billions of years. The keel is as old as the craton. They formed together, and they have endured together through everything that has happened to the surface of the earth in the intervening time. Above the keels, in the geological record of the oldest cratons, the dome and keel surface pattern of the early Archean gives way, gradually, to something that begins to look more like the products of horizontal tectonics. The greenstone belts of the Karpfal, around 3.2 to 3 billion years old, show deformation patterns and geochemical signatures that many researchers read as the fingerprints of something resembling subduction beginning to operate. The Isua belt in Greenland, older still, carries the ambiguous evidence that two groups of scientists read in opposite ways. And somewhere in the transition between these ancient terranes, perhaps around 3 billion years ago, perhaps earlier, the planet's tectonic regime shifted, gradually, irregularly, probably differently in different cratons at different times. from the vertical world of the stagnant or squishy lid to something more like the lateral world of drifting plates. Or perhaps not then, perhaps later. Perhaps some regions were operating in a plate tectonic mode, while others were still in a stagnant lid mode for billions of years afterward, and the globally coherent plate tectonic system we live inside today is a relatively recent achievement. Geologically speaking, assembled from a mosaic of earlier, smaller, more local experiments. The spread in the estimates, from 4 billion years to 1 billion years, may reflect not just disagreement about the same data, but the genuine possibility that the transition was long, uneven, and not the kind of single event that can be assigned a date. What is certain is that it happened. At some point, the slab pull took over. At some point, dense, cold slabs of oceanic crust began to sink at subduction zones in a self-reinforcing cycle, cold enough to be denser than the mantle, old enough to have lost their early buoyancy, massive enough that their weight dragged the trailing plate behind them and sustained the motion. At some point, the arc volcanoes that form above subduction zones began to distill continental crust in the same way the modern Earth does, adding new material to the growing rafts. At some point, the ocean floor began its current pattern of perpetual renewal, spreading at the ridges, cooling as it moves away, sinking at the margins, recycled within 200 million years. The entire ocean floor replaced every few geological cycles, while the continents above it remember a history 4 times the age of everything beneath them. The ocean floor forgets. The continents remember. There is something very still and very large in that contrast, and it is worth staying with it for a moment before the night closes in. The ocean floor you would find beneath any ocean on Earth today, the Pacific, the Atlantic, the Indian, the Southern, the Arctic, is nowhere older than about 180 to 200 million years. The oldest ocean floor, the remnants of ancient seabeds that have not yet been dragged down into a subduction zone, dates to the Jurassic period, to the time of the large dinosaurs, to a world that is almost unrecognizably ancient in human terms, and yet, in the timescale of the planet, is geologically recent. Everything before that has been recycled. Every ocean floor, from the Triassic, the Permian, the Carboniferous, the Devonian, the Silurian, the Ordovician, the Cambrian, all of it gone. Subducted, returned to the mantle. Lost, but the land remembers. The Acasta Gneiss is 4 billion years old, and it sits in the Canadian Shield, above a cratonic keel that has kept it stable since before the Cambrian explosion. Before the emergence of complex multicellular life, before virtually everything we associate with the history of living things on Earth. The Pilbara Craton in Western Australia carries crust nearly as old, dome and keel structures 3.5 billion years in the making, the fossil geometry of a planet whose tectonic engine had not yet found its modern form. The Karpval in southern Africa preserves some of the same ancient signatures, the same deep roots, the same testimony to a world when the problem of land was not yet solved and the water was everywhere, and the question of where the first shore would rise was still, in a very real sense, open, and inside a bank of younger sandstone in the Jack Hills of Western Australia. Inside a rock that is itself approximately 3 billion years old, there are crystals that are 4.4 billion years old. They were eroded from mountains that no longer exist, from rocks whose names we will never know because no coherent sample of them has survived, from a surface that was destroyed and remade so many times that the only witnesses left are these microscopic grains of zirconium silicate, nearly indestructible, carrying in their oxygen atoms the memory of liquid water and in their uranium to lead. Ratios the memory of their formation in a cooling magma in a world that was already, astonishingly quickly after its catastrophic birth, beginning to find a way to make itself habitable. The hellish Hadean, the name given by Preston Cloud in the early 1970s, drawing on Hades, the classical underworld, reflecting the assumptions of a generation of scientists who had not yet been able to measure oxygen isotopes in 4-billion-year-old crystals. The name stuck. It is still used, still useful as a label for the first 500 million years of Earth history. But what it conjures, that image of unbroken magma, of a surface entirely covered in glowing lava, of fire from horizon to horizon and no water anywhere, is a dramatization that the evidence has quietly, methodically eroded. The Hadean was hot. Parts of it were certainly hellish by any reasonable definition. But the crystal says it was also, quite soon, cool enough for water. And where there is water, and where there is heat enough to drive chemistry and distillation, the conditions for everything else, for crust and land and perhaps even for life, become imaginable. The first land did not rise from fire. It rose from water. It rose slowly, patiently, from a near-global ocean that covered a planet that had barely begun to cool, through a process of chemical distillation that took hundreds of millions of years and that we do not yet fully understand, through the accumulation of buoyant material that floated because it was too light to sink, anchored by cold, deep keels that hung beneath it in the mantle like the weight beneath a fishing line, keeping it stable through every subsequent geological upheaval. The first shore was an anomaly in a world of water. The first beach, if there was a beach, if the freeboard balance had tipped enough to expose rock to air rather than leaving it drowned beneath a shallow sea, was a small and temporary victory of solid ground over an ocean that still covered most of everything. And everything that has happened since, every mountain range, and every river delta, and every continent, and every island, and every valley, is an elaboration on that first, improbable emergence. The ground beneath you has been here, in some form, for billions of years, anchored by roots you will never see, buoyant in a planet that would otherwise swallow it, surviving by the accident of its own lightness in a world that has been trying to recycle everything for 4.5 billion years. The plates move slowly now, a few centimeters per year, carrying the continents in their patient drift. The mantle convects beneath them, cooler than it was, quieter than it was, having shed the enormous heat of the young planet over geological time. The cometites no longer erupt. The stagnant lid, if it ever fully dominated, gave way long ago to the horizontal world of spreading and subduction. The dome and keel patterns of the oldest cratons are fossil geometries now, records of a way of moving that the planet abandoned, or perhaps never fully had, and replaced with something else. But the oldest crust is still there, still floating, still anchored. The Jack Hills still rise from the red landscape of Western Australia, and inside their sandstone banks, older than anything else we have found from the surface of this planet, the zircon crystals wait. They have been waiting for 4.4 billion years. They will wait considerably longer. And inside them, in the ratio of one isotope of oxygen to another, in the chemical record of a cool magma crystallizing in the presence of water almost incomprehensibly long ago, the first chapter of the planet's surface is still legible, still speaking, still patient. If you are somewhere in the world tonight, and the question of where the first land rose has carried you this far, through the crystals and the cratons and the keels and the unsolved question of when the plates first moved, then you have spent this hour inside one of the most genuinely open and genuinely astonishing stories the planet carries. There is no neat resolution to offer, because the honest answer to when the engine started is that we do not yet know, and the honest answer to what the first shoreline looked like is that we cannot say. And the honest answer to whether something was already living when the first granite dome rose above the early ocean is that the evidence is there, in a crystal, and it is contested. And the question remains open in the best possible way, open not from ignorance, but from the sheer difficulty of reading a record 4 billion years old, carried in grains of rock so small you could lose them on a fingertip. Tell me where in the world you are listening from tonight. Wherever you are, in whatever latitude and whatever darkness, you are sitting on a craton, or on rock that was once part of one, or on sediment eroded from one over hundreds of millions of years. You are resting on material that floats by the same principle that the first continental crust floated 4 billion years ago. The ground beneath you is not the starting point of the Earth's story. It is a survivor of it. It is the exception that endured while everything denser was swallowed back into the planet. And it has been waiting, patiently and silently, far longer than anything alive has been here to notice it. If you are new here, there are more slow stories of this kind, careful descents into deep time and quiet wonder, written for the hours when the world outside has gone still. They will be here whenever you want them. For now, let the cometites cool. Let the ancient oceans settle. Let the dome and keel cratons stand in their stillness, 200 kilometers of depleted keel hanging beneath them in the dark of the mantle, holding everything up. Let the Jack Hill zircons rest in their sandstone, 4.4 billion years old and untroubled by the night. You have done enough for one day. Whatever questions remained open at the beginning of this hour can rest as well. They have been resting in the rock for longer than there have been eyes to read them, and they are patient beyond anything our language was built to hold. Let the deep thoughts settle and let yourself sink with them. Good night. Sleep well.